Hello everyone and welcome to Algebra 2. This is the beginning of Chapter 6, 6.1 Exponential Growth and Decay Functions, and we're going to do 6.2, the natural base e, at the same time. So our first step is going to be to match each exponential function with its graph. And the little tip there is to plot a point or two if necessary. So if you want to try and figure out which each of these are, that would be great to do on your own, but of course, I am going to do it for you. So whenever I get a graph of something that I don't recognize, my first step is to make a table. So for number 1, I say x is 0. Anything to the 0 power is 1. X is 1. 2 to the first is 2. When x is 2, 2 squared is 4. So I can see that it's rising, which rules out e and d and b. And then I'm going to look for those specific points. This one has 0, 1, and then at 1, it's already up to 5, so that's not it. And then 1, 2, this is promising, 2, 4, this is it. It's A. Now, before I go ahead and plot points again for number 2, how do I think that this is going to change? If it's 3 to the x, is it going to have the same shape? Of course it is, because it's also going to be rising. But even more importantly, it's going to be steeper, because when x is 0, you'll still be at 1. But then when x is at 1, you'll already be at 3 instead of 2. So let's see if we can find the one. Here it is, 1, 3. And what would it be if we could reach it? 2 would be 9. It doesn't even go that high. So this one's going to be F. And of course, there's only one choice left for ones that are going up. Let's see, C is the last one to be going up. But again, an easy point to check is when x is 1, I should get 4. And at 1, it is 4. So this one is C. So why are the other ones fractional? Why are the other ones fractional matching with the ones that are going down? Because what happens here is because, well, the first point's actually still the same. Anything to the 0 power is 1. But then when you raise 1/2 to the 1, you get 1/2. But when you raise 1/2 to the 2, you get 1/4. It gets smaller over time. So now I have B, D, and E, and this is going to be really hard to find points like 1, 1/2. They all kind of look similar. So believe it or not, it's actually easier to check negative points. When x is -1, what do I get? So when x is -1, I'm going to do it off to the side here. 1/2 to the -1 is 1 to the -1 over 2 to the -1. And hopefully you remember that when you have a negative exponent in the numerator, you can move it to the denominator and make it positive. Or when you have a negative exponent in the denominator, you can move it to the numerator and make it positive. So 1/2 to the -1 is actually 2. And negative, if I let x be -2, 1/2 to the -2 is going to do the same thing. 2 to the -2. So this is going to go up, and this one's going to go down. And I get 4. So I'm looking for one that at 0 is 1, but at -1 is 2. Not that one. -1, 2, -1, 2. Here we go. So this one is D. So you can figure these last two out on your own the same way. But what I really want to do is make sure that you see a couple connections between all of them. And that is that on every single one of them, the y-intercept is 1. That's because in exponential functions, anything to the 0 power is 1, whether this is a fraction or a whole number, so they all go through that point. But all of the fractional ones will be going down, where all of the whole numbers greater than 1 will be going up. And that's the general formula. That's going to be the standard for what we're going to be looking at today. The bigger this number, as it got bigger, the steeper, look how much steeper this got. But then conversely, the smaller this number, then the steeper it was in the other direction. So here's a little summary of things that I just talked about. If you have the function f of x is equal to b to the x, b does have to be greater than 1 for this to work. Then your general shape is going to look like this. It's going to pass through 0, 1, and it's going to have an asymptote. An asymptote is a line that a graph approaches more and more closely. And we're actually going to go back to this one to show you that. So when we first started to make this graph, we of course chose numbers like 0, 1, and 2. If we had chosen -1, 2 to the -1 is 1/2. And then 2 to the -2 is 1/4. 2 to the -3 is 1/8. So you see how it keeps getting smaller and smaller and smaller? But even if I do -10, it's never actually going to reach 0. It's going to get smaller and smaller and smaller, but it'll never be negative. It'll just get really, really, really small. And that's what an asymptote does. It guides the viewer to see that the graph gets really close to something without actually touching it. And we call that an asymptote. All right, so let's actually do some examples here. Try to graph y is equal to 2 to the x and y is equal to 4 to the x on your own, and then state the domain, the range, the asymptote, and the y-intercept. Of course, I am going to do them for you, but let's just make sure that you understand them. So a super quick table, 0, 1, 2. Anything to the 0 power is 1. 2 to the first is 2. 2 squared is 4. 2, 1, 2, 3, 4. There's an asymptote right there. So if you understand what the graph is going to look like, then you don't need to plot more points in the negative direction. These points will suffice to give you the shape. The domain is all real numbers. You can let x be anything you want. You could let it be -8. It's just that 2 to the -8 is a really tiny number, but you can let it be that. But the range is that y is always going to be greater than 0. It will never go into the negative area. My asymptote is a horizontal line, which means it has y is equal to, remember vertical lines are x is equal to a number. Horizontal lines are y is equal to a number, in this case 0. And of course its y-intercept is 0, 1. It's always going to be 0, 1 until we start shifting the graphs up or down, left or right. If you still haven't tried one on your own, you should definitely try number 4, or number 2 with the 4 to the x. So again, anything to the 0 power is 1, 1, 4. And look at this. You're not going to have to plot a lot of points. Already by 2, I can't graph it. So here's my 0, 1, my 1, 4. My asymptote is still at 0. And I'm going to go like this. Now here's a place where a lot of kids go wrong. They make this line and they don't pay attention to the fact that you can't cross 2. At 2, it should be all the way up at 16. So if you have 2 crossing at 10, then you've made a mistake. So let's go ahead and erase that and make sure that I stay on this side of the 2. So you'll know you did it right if it's steeper. The bigger this number is, the steeper the graph should get. But my domain, my range, my asymptote, and my y-intercept all stay the same. Okay, the base doesn't matter. So it is almost the same for a decay function. Now, a decay function is going to mean that b is between 0 and 1, so some kind of fraction less than 1. So again, we can go ahead and graph this. Anything to the 0 power is 1, but because if you put a 1 in, you're going to get 1/2, which is not going to give you this side of it. where it has the asymptote is easy to graph. Where you need the good shape is on this side. So unfortunately, you do have to get the negative, but it's just going to flip it. So at -2, then you can flip this 2 and do 2 squared, and it's going to be 4. And then 4. So it looks like that. Okay. Our domain is still all real numbers. Our range is still y is greater than 0. Our asymptote is still y is equal to 0. And the y-intercept is still 0, 1. So again, the base doesn't matter. 0.25. So this is the same as 1/4, which might be easier. And I'm just going to show you an alternative way to do it. Some people really struggle with this -1 and how that produces an answer of 2. So another choice is to change this to 4 to the -1 and then making this 4 to the -x. Then when you make your table, it's much easier to see. Anything to the 0 power is 1. But now you can pick -1 and you get 4 to the -1, which is 4 to the +1. So if that feels a little easier to you, I'm just giving you some choices. 0, 1, 1, 4. Again, I can't reach 216. Maybe put a little point up there to remind yourself how to draw it. And what is my point with this domain range asymptote? I'm trying to keep showing you that these graphs all have the similar features. The domain can be anything. You can plug in any number you want to for x, but the range is always going to come out to be greater than 0. My asymptote is y is equal to 0, and my y-intercept is 0, 1. Okay, so let me show you how exponential functions can be seen and are used in the real world. Some real-life quantities increase or decrease by a fixed % each year. The amount y of such a quantity after t years can be modeled by one of these equations. The top one is for exponential growth and the bottom one for decay. Our a is going to be the initial amount, r is going to be the % increase or decrease, and we're going to call the 1 plus r the growth factor, or if it's 1 minus r, the decay factor. So let's jump into a problem. In the year 2000, the world population was about 6.09 billion. During the next 13 years, the world population increased by about 1.18% each year. Write an exponential growth model giving the population y in billions t years after 2000. Estimate the world population in 2005, and then estimate the year when the world population was 7 billion. So this is going to be our population in billions. And it's going to start out at 6.09 billion. So I don't need to make this number in billions. It's already decided by the y, times 1 plus. Now be careful here. I need to change this to a decimal. So I'm going to move the decimal place over 2. So 0.0118. 0.0118 to the t. And that was the first question, A. Write an equation. And now I want to find the world population using my equation in 2005. So y is not a good way to indicate here. Instead, I'm going to switch my notation to f of 5, and that will indicate the year 2005. So 6.09 times 1, and I can actually rewrite this as 6.09 if you would like. Just adding those two together would give you 1.0118 to the t. So that's what I'm going to do here. 1.0118 to the 5th. And of course, you can do that on your calculator. The answer will be 6.458. But don't forget your units. It's not 6.458 people. It's 6.458 billion people. which would look like this if you wrote it out: 6,458,000,000 people. And then part C, estimate the year when the world population was 7 billion. So now they're giving you the why. When is it 7? And it's your job to figure out what the t is. Now, in order to do this, you need to know about something called logarithms, which we're going to learn later in this chapter. But for right now, since you don't know logarithms, we're going to solve this on our calculator, which is always a great way to solve an equation that you don't know how to solve algebraically. So I'm going to plug this in as y1 and this in as y2. So I've plugged my 7 in as y1 and my equation in as y2. Now, sometimes the most difficult part about all of this is making your window. So you want to consider what the window represents. This x value represents time. And since this function, it says, is only good for the next 13 years, I can make my window go from 0 to 13. That's how long the function is valid for. And then in terms of y, I'm trying to figure out when it's going to reach 7 billion. So I need to go at least as high as 7. Now I see that it's already at 10. I'm going to go ahead and leave it there. That way I can definitely see the whole graph. So I hit graph, and there's my y is equal to, there's my y is equal to 7. And it does hit. It's a little bit hard to see where. So I'm going to go ahead and use my intersect function and see if it can find that point for me. There's my first curve, second curve. It asks for a guess, but I'm not going to make one. Let's see if it finds it. It does at 11.8. So it's hard to see visually, but your calculator can see it just fine. 11.8. So we got x is equal to 11.871. Remember that represents the number of years after 2000, the year 2000. So in other words, it would be sometime during the year 2011 that the population reached that, partway through the year. Let's do another one. The value of a car in thousands of dollars can be approximated by the model given here. T is the number of years since the car was new. What is the annual percent increase or decrease in the value of the car? So remember that the function is supposed to be written as a and then 1 plus or minus r to the t. So since this is a 0.85, it must have been 1 minus 0.15. That's how you'd have gotten 0.85. So the value in thousands, it must have started at 25,000. That's what that represents. And its decrease is 15% every year. So even though you see a 85 here, it does not decrease in value 85% every year. That would be terrible. You always have to remember that this is 1 minus the actual decrease. In other words, it retains 85% of its value every year. When will the value of the car be 8,000? So I want to know the year. This is just like the one that we just did so that you get a chance to practice it. Actually, I was going to write 1 minus again, but there's no reason. I'm going to put it back to the 0.85. That is easier. To the t. So you're going to let this be your y1 and this be your y2. Now let's talk about the window again. So it would be really easy to think that your graph had to go all the way up to 8,000, right? But remember, this is in thousands. So you actually only want this number to be an 8, not an 8,000. And that's sometimes where people go wrong. So y1 is just equal to 8. Probably the biggest trouble that people have is recognizing these units. So what would your x min be? Well, x is dealing with years, so you can start at 0. Your x max, I don't know, could it take 10 years? Could it take 20 years? You could start with 10, and if you don't see, the answer, you could move to 20. And then for your y min, it's not going to be negative dollars. But since we know that the cost is going down and it starts at 25,000 and goes down from there, and you want to see it at 8, you really should maybe go all the way up to 25 so that you can see the start of the graph, and then you can figure out where it crosses at 8. And I will be looking for this answer in your notes because it's just a matter of plugging it into the calculator and using that intersect feature, and I want to make sure that you can do it. Moving on to compound interest. So consider an initial principal P is deposited into an account that pays an annual rate of R, as before expressed as a decimal, not as a percent, and it's compounded n times per year. The amount A in the account after t years is given by this formula. So the bad news is you must memorize these formulas for your quiz and test. But right now we have it right there. We're going to plug it in. So you have deposited your principal, your deposit is going to be 9,000. It doesn't say that it's measured in thousands, so we actually want 9, times 1 plus the rate, but as a decimal. So remember, move that over 2. So it's 1.46. You're going to move that over 2 places. So 0.0146 over, and then the n stands for number of times a year. So if something happens quarterly, that means it happens 4 times a year. If something happens monthly, that means it happens 12 times per year. And if something happens daily, that means it happens 365 days per year. So we're actually going to do this problem 3 times. First, we're going to do it quarterly. And then up here, we're going to use that 4 again. And it says find the balance after 3 years. That's our t. T is equal to 3. All right, I think you're really going to like how we do this. So I have my 9,000, and I'm going to do parentheses, 1 plus, remember to make a fraction, alpha, F1, and then enter, and we'll create your fraction, 0.0146 over 4, and then I have to move that arrow key over to get the other parenthesis to the 4 times 3. And I hit enter. And I get $9,402. So he did good. After 3 years, he got an extra $402. That's kind of nice. Now here's the really fun part. If you hit second and then enter, second and then enter, it'll repeat exactly what you just wrote. So instead of having to write it again, now you can put that 12 in there. Now, unfortunately, it does start to overwrite, but you can use the insert button, which is above delete, to get that not to overwrite. And then if I go over, right there, I can just overwrite this one with a 12, and now I've changed it to monthly without redoing the entire equation. So from our calculator, we got this first one, the quarterly, if you did it quarterly, how much money you would have at the end, as $9,402.21. And then when we switched it to monthly, he actually got $9,402.71, 50 cents more. And then I did ask you to find this number on your own, so I'm going to go ahead and let you fill that in to show me that you understand how to do that. But let me use this opportunity to explain what these numbers mean. So if you went to the bank and they just took your money and they gave you the interest at the end of the year, the reason the 1 is there is that's because you want to get your same money back. So you're getting 100% of your money back, plus you're getting your interest, which in this case is 0.0146. And they're going to keep giving you money back plus interest for every year that goes by to the third. When they say they're going to compound it, that means they're actually going to stop after 3 months, if they do it quarterly, and they're going to calculate how much money you're supposed to get and give it to you, or at least put it in your bank account. And then when they go to do it after 3 more months, when they calculate it, this starting balance will be a little higher because they already stopped and gave you some money at the beginning of the 3rd month. And then at the beginning of the 6th month, you'll have even more. And at the beginning of the 9th month, you'll have any more. So it seems like a good deal, especially if they say, you know what, we're going to stop and figure out your interest every day. Then you can be building interest on your interest. So as you can see, it does improve if they give you interest on your interest. And this is what compounding is. However, it does have a natural limit. So even though this isn't here as a question, what if you compounded the interest every hour of the day? Then how much money would you have? You would have $9,402.96. By the way, now you know that this answer should come out in between 71 cents and 96 cents. Or what if you did it every minute of every hour of every day? Then you would have, hold on, you would actually still have $9,402.96. This has started to become, the difference is way out here in these numbers here. And because we only round to the nearest hundredth for cents, you don't see them. So the bottom line is there ends up being a limit. And that limit is what will help you understand something called the natural base E. So it's a little weird. The letter E is actually a number. E is approximately 2.718, blah, blah, blah. But this is the important part right here. From that little formula we were just doing, you have 1 over, and then you are putting the number of times per year here. So we're just going to call that X. And then we were raising it to a power that was also based on N. And what E is the limit of this as X approaches infinity. So as X just gets bigger and bigger and bigger, or in other words, for an example like continuously compounded interest, you're just continually compounding it, not just every day or every second or every hour, but every single nanosecond of every second of every minute of every hour of every day. This limit turns out to be this number E. So because E is just a number, you must always keep this in mind, that E is just a number. The E graph looks just like any other exponential growth graph, because you can think about it as 2.7 to the X. And you know that that's what it looks like. Similarly, if you think of this as just 2.7 to the negative X, then it's going down. So I definitely want you to know this basic shape, and I want you to know that in the same way as anything else, anything to the 0 power is 1, but when it's actually E, which is what it actually is, E to the negative X, or on this side, E to the X, when you have 1, then you can think of that as 2.7. Okay, they wrote 2.718, but you're not graphing 2.718 any differently than 2.7. We're not going to get too deep into graphing the E function, but I just want to remind you that it is going to be, like I said a minute ago, it's going to be just the same. So it's going to have an asymptote right at y is equal to 0, unless it moves up and down, which none of these do. So the graph is going to have an asymptote at y is equal to 0. And then normally it's going to cross at 0, 1, unless it has an A. This one's going to cross at 2, and it's exponential decay. So it's going to look something like that. And then this one crosses, instead of at 1, at 0.75, and it's exponential growth. And you could make it a little steeper. It's definitely growing a little faster there. But again, I'm just looking for general shape and understanding. This one, again, anything to the 0 power is normally 1, but when there's a 5 in front, I'm going to multiply by 5. So it's going to be way up there, but it still follows that asymptote. And finally, this one. Again, anything to the 0 power is 1, but when we multiply by 0.8, it's going to cross at 0.8, and this is negative and a little bit steeper if you wanted to try and draw that. You could try and draw a little bit steeper there. Okay, but basic shape, where the asymptote is, where the y-intercept is, that's what I'm really looking for. General shape, y-intercept, and asymptotes. So there's a couple really great applications of E. One of them is it's often used for population functions. Another one is used for continuously compounded interest. So we're going to go ahead and do a couple problems so that you can see some applications of this number that we call E. So the first one, the population of Evans City is currently 48,500, and it's declining at a rate. So be careful when we change this to a decimal. Not only are we going to move the decimal over 2 places to 0.025, we're going to make it negative. You can model the population of Evans City by the equation P sub t is equal to P sub c e to the RT. So PC is going to be our current population. PT is going to be the population after t years. R is going to be the decimal rate of decline. And our job is going to be to predict the population after 25 years. So the population after 25 years is equal to the current population, 48,500, e to the negative 0.025t, which there's another 25 now, but this one is for years. And you can go ahead and just type that into your calculator. There is an E button right on there, and you should get 25,960 people. So it's a very easy formula to use. Number 2, your parents will need $25,000 in 10 years to pay for your brother's college tuition. They can invest in an account with an interest rate of 9.8% that compounds continuously. How much should your parents invest today in order to have your brother's full tuition available in 10 years? So first of all, this is the key. As soon as you see that something is compounded continuously, you know you want this formula. A is equal to P e to the RT. That's up on your paper there. So in this case, the amount that they want is 25,000, and they're trying to figure this out, how much they should originally put in. It's called the principal, but we're just going to write it as P, and then E to the, remember to convert that, 0.098, and then times, they want to get this within 10 years. So you can divide this by E to the 0.098 times 10 on both sides. And if you can type this into your calculator accurately, then you're all set. But I am going to do it for you just in case you're not finding that button or you still don't know how to use the fraction key. Don't forget that I will not answer the question during a quiz, how do I type this in? Because I'm showing on the video and I expect you to actually figure it out. So there's the answer. Hopefully you can do it on your own and skip over this next part of the video. So I'm going to do alpha F1 and then enter to get my fraction. And then I'm going to type in 25,000, move my arrow down to get to the bottom of that fraction. The E button is right here next to the 4, so I do second. That gives me my E to the X, 0.098 times 10. And then it looks just the way I want to, so I can feel very confident that the answer is right. Remember, though, this is in dollars, so we round to the nearest cent. So it's $9,382.78. On this next part, you can simplify expressions with E in the same way you would with X. So if this had been x to the negative 9 times x to the 12, then you could write it as, when you multiply like bases, you can add their exponents, x to the third. So this is literally just going to be e to the third. Now, of course, you know what I'm going to say. I want you to try the next 3 on your own, but of course I am going to do them for you. So when you have 2 different parts like that, you can do the numbers with the numbers. So reducing that becomes 5 over 7. And then I have 2 e's on top and 7 on the bottom. if you think about it that way, then when you get rid of as many as you can, there are 5 left on the bottom. Or if you did it by subtraction, then you would have gotten 5 over 7 e to the 2 minus 7, which is e to the negative 5, and then hopefully moved your negative exponent to the bottom and made it positive. So it just depends on how you look at it. When you have a power to a power, you multiply them. So this is 2 to the 5th because this is 1, so 1 times 5. And then e to the negative 3x times 5, negative 15x, times 2e to the x plus 1. So numbers with numbers now gives me 2 to the 6. And again, when you're multiplying like bases, you add their exponents. So it's e to the, adding those together is negative 14x plus 1. Or if you want to multiply that 2 to the 6 out, it is 64 e to the negative 14x plus 1. And the last one, remember that a fourth root means it's something to the fourth in order to simplify it. So how many 2's would I need? I would need 4. 2 to the 4th is a perfect fourth root. And what about the e to the 24? Can you think of 4 perfect things that would make e to the 24x? Well, since you're adding their exponents, you're adding up 4 things that make 24x. Each thing must be 6x. Can you picture that? So e to the 6x, e to the 6x, e to the 6x. So this is also a perfect fourth root. It's e to the 6x to the 4th. And so this simplifies just to 2e to the 6x. The next one is just a thinking question. Which one increases at a faster rate? So for example, a line, y is equal to x, just goes up at a nice steady rate, where we know that a parabola goes up at a much steeper rate. Their question is, how does 2 to the x compare? Well, you could make a table if you were trying to figure it out. So we know the table for this is 0, 0, 1, 1, 2, 4, 3, 9. And then we could make a table for this one. 0, 1. So it starts a little higher, but that's not what they're asking. They're asking how does it grow. At 1, it's 2. And then at 2, 2 squared is 4. Look at that. I'm at the exact same spot. But then if I keep going with this one, 3, 8, still not better, right? 4, so I guess I'm going to have to continue this one. 4 squared is 16, 5 squared is 25, 2 to the 4th is also 16, and then 5 to the 5th is 32. Am I convinced yet? Hasn't been obvious yet. 6 is going to be 64. See, this is going to keep doubling. This is going to get really big really quick. Where this one is 6 squared, 36, 7 squared, 49. Now you can definitely see that it's outpacing it. So this 2 to the x is going to grow at a much faster rate. If you were going to try and draw it on here, it would be like that, very steep. So it not only starts out a little higher, but then it grows really fast. Average rate of change. So for average rate of change, when you see this phrase, I need you to be thinking slope every time. Average rate of change means slope. So what do you need to find the slope of something? You just need 2 points. They want to know the average rate of change in the population over the first 6 years. So that means they want you to start at year 0 and go to year 6. At year 0, to find this, I'm going to do P is equal to 6850 times 1.03 to the 0. Well, anything to the 0 power is 1, and then 1 times 6,850 is 6,850. And then for this one, I want to know 6,850 times 1.03 to the 6. So I'm going to quick type that into my calculator. 6850 times 1.03 to the 6 is 8,179.258. And slope is y2 minus y1 over x2 minus x1. So whenever you see average rate of change, this is always what they're looking for. 8179.258. And actually, if you really want your answer to be exact, you could leave all the other parts of that are in your calculator and just right away subtract 6,580, which we didn't round. That's an exact number. And then divide by 6 to get the exact answer. So minus 6850 and then divided by 6. That gives me 221.543. Now what does that represent? Well, the top number is our people, and our bottom number is in years. Year 0 all the way to year 6. 6,850 people up to 8,000 people. So this is people per year. It's average. So what that means is some years they might have gotten more than 221 people. Certainly there wasn't a single year that they got 221.5 people. You can't have half a person. But some years they might have done a little better than that and some years worse, but this was the average rate of change over the 6 years. Okay, so we've done this in every chapter. We've modeled, that means we've written the basic equation and then we've plugged in a point to figure out the value of b. So they actually gave us 3 different points, right? But we only need one of them. But since this one works for every value of b, that one's not going to be the best pick because anything to the 0 power is going to be 1. So I'm going to pick 5 instead. 5 is equal to b to the 1. There you go. B is equal to 5. What if we had picked the other point? 1/5 is equal to b to the negative 1. That would have gotten us the same answer. This means 1 over b. And then again, you can see that b is equal to 5. Okay, last one. So we're starting with the formula y is equal to a times 0.5 t over 28. And they want to know what percent of the chromium-51 decays each day. And this is a little confusing because we don't normally have this t over 28. It's just usually to the t. So that's exactly what we're going to do. We're going to fix that problem. We're going to change this to 0.05 to the 1 over 28 and then raise that to the t, something we don't normally do. I'm splitting these up. But now that I've done it, can you see how that would work? Because if you have a power to a power, you multiply them. And t over 1 times 1 over 28 is t over 28. So I've separated them back out. Now I can write this as 0.5 to the 1 over 28, which I can do on my calculator. So I get 0.9755 to the t. But in order for you to actually figure out the percent decay, this is the percent that's left. So remember that the formula is always 1 minus. So it's 1 minus 0.0245 to the t. So pretty much I'm taking a formula that's already been simplified and I'm unsimplifying it so that it's in the format that we're used to, because this is where you see the decay rate. And we actually have to do one more thing. It's already been put into decimal form, so the decay rate is actually 2.45%. Okay, that is it for sections 6.1 and 6.2. Have a great day.